noticed today we had quite a few different perspectives of what the, I wouldn't say single people's views of what's important for neural computation, but we've just heard asynchronous computing, we heard spike-based representation, we've heard about high-dimensional distributed codes, we've heard about analog, and so forth. So, does anyone up there have an opinion? We want to go out there of what the kind of primary one to tackle first is, because you can't do all of these at the same time. And I think a number of the different technologies pick a few. So who wants to step out there and say, this is the one we need to understand, implement first, and then we'll move on from there? Someone step up and say that. None of it's important? No one? Okay, who has an opinion of which is an important one?
I think they're all important, and we do need to do them all at the same time, right? So,
Plenty of people.
I can't remember what the list was. Nobody else with a view?
I like that answer. That was great. We do them all at the same time.
Well, anyways, yesterday we heard that there's 80 different kinds of neurons within a square millimeter, I think it was. And so we have all these different types of neurons, and we've learned that we can do all this neat stuff with continuous equations, learning rules that may approximate these other equations, but and a lot of the architectures are focused on maybe one aspect of that, but we saw there's great diversity in biology, and maybe it's performing all of these different things at once, but I guess which ones are important? Are we looking for just one canonical neural model, or how are we going to marry and put those architectures together and capture the diversity of all this different biological observations? Thanks.
What was the question?
All right, I can take a crack at that. I guess I think that the issue of it's not so much of an issue of the diversity that we know, but it's the one that we don't. So, if you give me a list of, here are my 25 neurons that I care about, it's not that difficult to build something that can do all 25, and you can pick which one you'd like. But the problem is, as soon as I do that, there will be 10 more, or 3 of those will be no longer important, and there'll be something else. That's why so for example, I would argue that's why, the Spinnaker approach is doing what it is.
That's right. That's what I would argue. That's why you leave that bit of the problem in software.
Yeah, exactly. So I think that's really the issue. If there's agreement, then then you can easily move forward. But I think the issue is that there isn't, in some sense. There's no convergence yet.
Maybe I could say something here. I feel that there is a big dichotomy between the way people coming at it from neuroscience look at this and people from IT. And I think that from a neuroscience standpoint, the emphasis is on functionality. And the question is, what is the logic of computation in the brain? And I think this is something which has to be pushed, at least from my standpoint, into the center, because in the end, what we would like to achieve, and we think we can achieve, we can build any simulator, we can, design big systems and all this. The question is, what do they do actually? So, for example, you take a simple, let's say, C. elegans or fruit fly or zebrafish, whatever your favorite model organism is, and you might be able to simulate it. The problem is that you don't know what it does. You can look at the data as long as you want to. You see all the data, and there's no way to interpret what it's doing. So the logic of computation is missing. If I turn this around and I look at it from an IT standpoint, What I see is this. We start with the Turing machine as our model of computation, and we seem to know what we're dealing with. If you look at it from a neuroscience standpoint, that thing is just missing. It's just not there. And if you ask a neuroscientist, it would tell you that the brain is not a Turing machine. But if you ask them what is it, there is no answer. Okay? So fundamentally, you look at all these circuits, and you don't know what they're doing. So I think that we have a fundamental problem from a functionality standpoint. And so maybe there is a need to focus on this problem a little bit more and put it to the top of the pile.
And to follow up on what Aurel just said, if you actually had that, it's not clear I would build neurons to compute. Right? So to use the Turing machine analogy, we don't. This is a Turing machine, yes, in the compute model, but it actually isn't computing like a Turing machine computes. We don't linearly scan the memory, right? We've built something else that happens to be equivalent, but is much more efficient. So if you actually knew what the model was, it's not clear to me at all. I mean, just speaking very pragmatically, what I would build to implement that model in the most effective way.
I have one suggestion. I think since we are lacking, as you just said, concrete information what exactly biological neural system is computing, I think it would help us as a community here in neuromorphic engineering if we would have a set of benchmark tasks, including also learning tasks, which are maybe designed for various reasons. Some of them more biologically inspired, some because there we want to drive really performance of the systems, where several people work on this. I think if we just look back at an analogy in machine learning, it was really instrumental to have in the 80s and 90s to have the Irvine database of benchmark learning problems. And I think something of this type, I think, would be very beneficial for this community.
So I had a comment on the learning rules you asked about. So in biology, if you notice, there is this whole temporal scale of application of these rules. I mean, so for example, long-term plasticity, spike timing dependent is one of them. Its interaction with short-term plasticity, which Paul Rhodes was talking about in his talk, enables bidirectional connectivity, for example, depending on, irrespective of the frequency of activation of the spikes. So these interactions in time scales are very critical to understand. And there is time scales from milliseconds to minutes and probably days. And so how does all this play into regulation of activity that allows for learning to happen is a very critical question. I don't think I know the answer, but maybe there are others who can comment on it.
I'd just like to add on to what Wolfgang just said. I'd love to have better benchmarks. I would vote that they have to involve time. They have to involve behavior, interaction with sensors. We don't need another MNIST. We need, behaviorally relevant benchmarks.
I would like to add one comment to this question about the diversity of neurons. I think one aspect where I see divergence between many designs, neuromorphic and biologic, is that inhibitory neurons really play a special role in neural system apparently, from kind of regulated oscillations like Fritz mentioned, but also, for example, from our perspective of self-organization of learning then, because they're really, it's when you have a competition of neurons, for example, for becoming expert or for responding to something, then really the timing of this competition is essential. And I think there are concrete hunches that even though different types of inhibitor neurons may have specific different roles in regulating this competition for plasticity, and so this would just open up the bag of tricks, maybe also more for neuromorphic engineering, if one would look at this interaction between exciter and inhibitory neurons.
Yes. Today we had 3 talks somehow dealing with issues of hyperdimensional computing. So Jeff is working with HTM, then Rod talked about sparse hyperdimensional computing, Penty, dense hyperdimensional computing. So my question is mainly to you who presented on this topic and working with this topic. How do you see on chances to get a more coherent theory of hyperdimensional computing? Whether, or maybe if there is a need for more coherent view on hyperdimensional computing?
Maybe you could elaborate what you think a theory might be, or I mean, there's lots of things to advocate for it, but I'm not sure what. And we have differences in commonality in our belief about these, but and we've written extensively in our work about the mathematical properties and the advantages of using sparse coding, and so have other people. So I'm not sure there's a universal theory there or not. Maybe Penty might feel there is, or but I'm not sure what it is you're looking for there. Does that make any sense? I don't know. Do you think there's a universal theory of sparse coding? I mean, hyperdimensional coding, I should say.
Well, the way I've come to think about it is the brain is too complex for me to try to simulate and get behavior that I understand so try something that you can understand and has some hope of shedding light. And if you get interesting behavior, and that corresponds to some human or animal behavior, and if your system is such that you can analyze and understand it, and that's why I was introducing or talking about computing in terms of some abstract or algebra, which then can be analyzed, then that could be, I mean, it has first of all, it has a chance of instructing us about how brains may compute. It may not, but it still may result in some interesting computational paradigms that let us design better computers for things that neither current computers nor brains are good at. So it's worth trying, and the thing is that we just have to jump in, experiment, try and see what happens. And first of all, we have to just learn how to use this kind of new set of computational tools. If you look at how digital computers were first used, they were just substitutes for analog computers that used patch boards, so they looked like an old telephone exchange. Then symbolic programming was invented and developed. Without symbolic programming, we wouldn't have these computers that we would. So some development like that is likely to happen when we just go and try to do things using some of the new ideas that have come up here and in this meeting.
I don't disagree with that, but I do disagree with it. I mean, I don't disagree with it from the point of view that it's worth doing what you do, Penty, and explore these ideas from that point of view. But where I do disagree is that I think we can't understand how neural tissue works, and many of the ideas underlying sparse distributed codes, which are hyperdimensional vectors, in your terminology, many of those ideas help us understand how the neural tissue works. And so I don't think you can take it from two different approaches. I don't think, that's why I'm wondering if there's a universal theory here. Your ideas going back to your book many years ago helped influence my understanding of how neural systems work. But I always started with the neural systems first and asked, what are the properties there and how do they work? And I don't want to abandon that. Well, you're taking it more from a pure point of view of what can we learn from studying hyperdimensional vectors in absence of a neural theory. So those are both valid approaches, but I don't think, I disagree that the brain's too complicated to understand. I don't think that's true at all, but they inform each other.
So maybe I can add here something from the perspective of neuroscience. I mean, in a way, in neuroscience, these ideas that you know, you have high-dimensional and distributed codes. I mean, it's basically, it's Hebb's theory. It was very much in Hebb's book. And so conceptually, you know, in neuroscience, people thought a lot about it, and there's kind of this dichotomy. So you have kind of these feature-based representations where you can take the activity of one neuron and you can interpret what it is in the outside world. And this works well in the periphery. You know, in V1, there's often an edge that corresponds to directly, you know, is to the firing of the neuron. But as you go higher up in cortex, this becomes much more complicated. And the question is, how distributed does the code get? And I think to some extent there is a theory around. And I mean, we are, you know, you have this feature-based representation where you can actually really look at a single component of your vector and say what it is, independent of the context of the other neurons. And the other extreme is actually an entirely distributed code. And there is, and of course, we have also computer science models for this. This is kind of hashing. So it's very interesting how the brain somehow transforms representations that are pretty feature-based, and you can locally interpret them, to probably representations that are more distributed. But I would say some theories around in computer science is basically, you know, between hashing and understanding more local codes.
I have a point to make on that, too. I mean, it's a rather open-ended question. I mean, how do we sort of, you know, get a more comprehensive theory? I mean, if you look at the experimentation history of neuroscience, I mean, you know, for almost all of the whole history, you know, the best information we've had, you know, in terms of time scale has been electrophysiology. You know, you get a millisecond time scale, but you only have ever been able to look at one or a handful of neurons in a volume. And so now we're at a period of time where, you know, calcium imaging is coming on, and which has a very slow time constant. And if you wanted to vet a theory like mine or any of the sparse distributed coding theories, you have to see whole sets of cells distributed over several hundred micrometers, but very sparsely, turn on and off within a couple of milliseconds of each other. So, you know, I think that the theory will be led somewhat by, or, you know, fleshed out by experiment in the next, you know, half decade, as people invent these, you know, voltage-sensitive dyes and so forth that can see whole volumes, you know, single cell activity over whole macro column-sized volumes at millisecond scale activity.
But even at the time rates we're doing it now, you can see that. I mean, there's this tremendous amount of evidence of the sparsity, and you know, that these encodings are changing. They're sparse and they're changing over time. Maybe not at the millisecond level, but I don't think there's any doubt at all the codes are sparse in the brain. I mean, this goes back for decades, and it's been validated over and over again. So I take that, you know, the idea that the brain uses sparse distributed codes is pretty much, in my mind, a done deal. The question is why, and what are the properties associated with that? And I think we have a lot of good ideas about that. We actually, I don't know if we have it if it might be, we have a paper in submission right now, a manuscript in submission, which is talking about the role of sparse coding in neuron operations, and I think it's on arXiv. You can find it on our website if you're interested in that.
But Jeff, I would say in neuroscience, it's not a done deal. There are still people who don't believe in sparse coding, and of course, you can record from an arbitrary neuron in V1, and very likely it actually will.
There's a funny thing about neuroscience, Fitz, is that every idea is contested. I don't know a single idea in neuroscience that is not contested. So yeah, I can find people who don't believe in anything. I mean,
but you have to look for them very long. That's what I'm saying.
Yeah,
so,
well, it's a pretty ordinary group. I mean, so but if you do a nice distributed sample from them, you'll find that there's some general trends, and the relative. There are certain neurons that seem to be more active than others, but in general, you find there's always been also a bias in measuring from neurons that fire. I think if you talk to most neurophysiologists, maybe not the ones you talk to, that they will agree that most neurons are relatively inactive most of the time, and then there are times when they're active. And that general paradigm has been, I think, well accepted. But you know, maybe I'm wrong, but I don't think I'm wrong. I mean, you can always find exceptions to this rule. So we have to be careful not to let the exceptions define. You know, we can't let them drive things. I guess I just disagree, pretty much.
I would like to make one comment. As a computer scientist and theoretician, I'm usually somewhat disturbed if one has a large focus on coding. Then it's something that's very popular in neuroscience. But for example, in computer science or circuit theory, there's very little work on coding because one knows if you have, for example, an efficient circuit doing a certain computation, this coding may be very opaque then, right? It may even look like a lousy coding circuit there. And I think one should avoid falling into this trap of analyzing computation in terms of coding and communication then. I think really efficient computation have often a different organization, and particularly we take into account the brain and many analog circuits. These are recurrent networks, so you're looking at dynamical system, you're looking at possibly self-organizing dynamical systems, and these concepts may not be the best concepts to analyze computations in these systems.
Maybe just add to that, I think there's interesting work in dynamical systems. So there's actually, there's now concepts in information theory that go beyond the memory-less feed-forward information channel. And so there's this work by Jim Crutchfield. And so I hope that actually some of these methods we actually could start to use. I think that's very interesting development. I mean, right now they are applying this mostly in very small systems, but it's kind of this kind of information theory of complexity and stuff like that.
So I'll just make a few comments, which, if some of you know me, you've probably heard me say these things before, but I'll try to say them briefly and then, see how many eggs you want to throw at me. So just so you know, I'm Todd Hilton. Those of you who don't know me, and I started the Synapse Project. So I'm a huge fan of neuromorphic computing, right? So I think it's great stuff, and I think it has great potential, both as a science and a technology, and as a future industry. So I'm very, very bullish on the whole enterprise. I wouldn't have spent so many years working so hard at it, along with many other people who did such a fine job. But I have certain reservations about our ability to do things like build a brain, and whether or not I think we are basically, and I think, Oral, you said it, that we're I say that we're conceptually impaired in some way, in translating sort of the things that we imagine that brains do into stuff that we can build and make it do what we want. So just a few thoughts. So on computers, to me it seems the big unanswered question is, where do algorithms come from, right? These are the things that the computers do. And clearly they come from us. The computers themselves don't make algorithms, at least not yet. And so that's, I think, a very fundamental question that we don't really have an answer for. In fact, it doesn't really even show up in the field of computer science. Where do algorithms come from? So on the topic of brains, it seems to me that brains are kind of, for lack of a better term, they're an engine that creates organization, okay? And so it seems to me somewhat contradictory or ironic that we would be looking at brains in gruesome detail for the organizations that already exist within them as a way to explain how they work, when what we actually want to know is how did that organization come to be to begin with? Okay, so in other words, the question is, not what are the parts that make the brain works, but what are the things that made those parts come to be, all right? And with that sort of perspective, I can't escape the thought that, brains aren't the only things that sort of organize themselves in ways that we don't understand. In fact, I would argue that we don't know how anything organizes itself, and everything actually does. So I've also always been struck, by the idea that for some reason, everything fits together in the universe. I mean, it's all here and it all fits together somehow. And the only two explanations I can think for that is that there's a creator who really does, put every molecule in the right place. I don't find that to be a very workable proposition. But the other proposition is that it all fits together because it came from a common origin and evolved under some common principle. okay? And for that reason, everything fits. Otherwise, I can't explain why everything comes together. So the point there is that if you're asking the question, how does the brain organize itself, I think you're also asking the question, how does everything else organize itself? Okay, and the advantage of that perspective is that by looking maybe at many different things other than the brain, which also organize themselves, which is, I think, absolutely everything. I mean, we're talking galaxies and social systems and economic systems, and everything organizes itself. Maybe we'll find a common principle so that when we want to go and build the brain-like artificial thing, which is a word that I hate, that we'll have a basic principle. And maybe it won't be neurons, right? The way in which we choose to implement it may have nothing to do with neurons. It may have to do with some simple way of capturing this principle into a technology that we can build, right? So now I want to say what I think. So with that said, and I'll try to close with a more optimistic tone. It's not clear to me that the thing that we want to do is a computable thing. Okay? Not all things are necessarily computable, and I don't know if this is computable. I mean, I certainly hope it is. It's the thing that I think about all the time, but it's not clear to me that it's a computable problem. So the bridge is, and the hope is, and maybe part of the place that we get confused is that when we think about the problem of self-organization, say, in a brain today, it usually comes across as, you know, what's the learning rule, okay? Or what are the dynamics of the components that go into the model? But the models are essentially, when they work anyway, they are basically a parameterization of an optimization problem for which we can write some sort of algorithm which reduces the cost function or whatever the other optimization technique is you want to use. And that's what we think of as learning and self-organization in a practical sense. That's what we can do. Now, is that sufficient? Can that idea describe all of these other things that I said? I don't know, okay? But that was I just wanted to sort of lay that out there maybe to give you all at least my own perspective on the problem, and you're happy to, get feedback from all of you. Thanks.
Maybe I can start to argue about some of the things that you mentioned. So one thing I believe is that brains, more important than saying brains organize structure, I think the ultimate goal of brains is to produce behavior. And so if we start by trying to tackle problems which are more tractable, like how to build small engineered systems that produce behavior in intelligent ways, then maybe we can find some of the underlying principles. And I think we're going to find different principles depending on the different problems that we want to solve, or depending on the different behaving systems that we want to build that will then solve very specific problems. I don't think there's going to be a one-size-fits-all solution to building a general purpose, super intelligent brain.
That lives on Mars.
I have a question, if I could ask.
Are we off that topic already?
What do you say?
Are we off that other topic already?
Yeah, I think Todd had his chance with physical intelligence. Where are you, Todd? How'd that? Yeah, no, we can talk about that more. Would you like to respond?
I have so many things I could say, but I'm happy to go on another topic.
No, please do.
Just a few quick things. First of all, you're mixing up two things. One is the study of complex systems. And if you're interested in that, go to the Santa Fe Institute, and that's what they do there. Now, the brain is an example of complex systems, but to understand how the brain works, you don't need to understand all the nature of complex systems. Second of all, the brain is not a self-organizing system. It has huge amounts of structure at birth. It's not coming out of an amorphous blob. And the way you can think about the brain, you can just think of it as a memory system. It's a very unusual type of memory system. It takes in and it stores patterns and it recalls patterns. You can understand the entire thing that way. And you don't have to get misty-eyed about the whole thing.
I would respectfully.
Well, you went on for a long time, so okay. We're just getting a couple of fronts here, right? So It reminds me, I used to run Redwood Neuroscience Institute. When we had these conferences, we would bring in people for these workshops. And I remember going around to all these theorists, these neuroscientists, And I said, how long do you think it is before we have a comprehensive theory of the neocortex? How many years? And then there was, people say, 50 years, 100 years, 500 years, 30 years. Some people, like 5% of the people said never. And I said, what the hell are you doing as a neuroscientist? If you really don't believe you can't figure this thing out, why are you here? Well, it's a good job, but I enjoy it. I don't have patience for that. I really don't. If you don't think the system is solvable, if you don't think we can do this, you should be doing something else.
So a few comments. First of all, I did say there was reason for hope. I just said I wasn't sure. I don't think you're sure either, so I'm just admitting my own, I think. But my other point, though, about the brain already coming with a lot of structure, of course it does. I mean, we evolved over long periods of time, but it's the same question, how did all that structure come to be that led to the other thing?
Then you go to the Santa Fe Institute. We don't have to answer that question here. We don't have to answer how genes create a phenotype. We don't have to answer that question at this conference. I don't think that's our job. It's a very interesting question. But I don't think it's relevant to the question of how to build brains and how do they work and how do you build neuromorphic hardware. I think it's a separate question.
Well, in some ways it is. I'm suggesting only that if there's a common organizing principle, it might help to look at something else as well to look for the commonalities. It might.
That's a very good idea, but I don't think it's a necessary requirement. And it's interesting how the Santa Fe Institute had been trying to do this, look for the common principles underlying all complex systems. And I think they found it harder than they originally thought. I don't want to speak for them, but it's a challenging task. I just don't think that's an interesting thing to pursue. And if some people want to pursue it, like, okay, let's get to the nature of all complex systems, I would encourage that. It's a very interesting topic. I don't believe we have to solve that for the task we are assembled here for right now.
Well, I don't understand it because you just said the brain was a complex system.
Yeah, but it doesn't mean I have to understand the principles underlying all complex systems. I don't need to find the uber principles about complex systems. We can understand this one perfectly well without understanding how it relates to market economies. But by the way, this is a topic I think about a lot, and I think I actually understand some of those principles. But I didn't want to make that argument here. There are principles of hierarchy in complex systems, there's principles of time-based patterns, and there's actually a lot of principles with sparse distributed codes and how you can sample from large populations and get to understand the things that are going on. But I don't think that's the purpose of this conference. I just didn't want to leave it on the table that you have to do that before we'll figure out how brains work. I don't think you have to do that.
May I?
It's just a personal opinion. I just don't want everyone to think that it's a requirement.
Yeah, I like to follow up on Todd's question in a different way. There are a lot of us in neuroscience who believe that the fundamental substrate is a combination of sensing with locomotion. And that intelligence is something which has been built on top of that. So if we understand sensing, integration of sensing, and then some kind of a motor control, then we're going to be a long way in understanding actually how brain works. Because possibly the rest as a principle is going to be built on top of it in the space created by this. So then may I suggest that we become a little bit more modest and we don't talk about intelligence. We retreat from that for the next X number of years, and actually we focus on this fundamental question, and then, depending on what space we are creating there, then maybe we can attack the intelligence problem. For a lot of us, intelligence is fiction. We don't understand, how to go about it in any way. And there are no neural correlates for this in any way. And just to make it much simpler than this, I sort of believe that in the space of neuromorphic engineering, the big elephant in front of us is memory. We don't have an idea how to deal with this in the analog domain. And in neuroscience, we also cannot point what are the neural correlates of memory. We don't know where it is. We don't know how to write it. We don't know how to read it. And now going back to the Turing machine idea, okay, which we are all familiar with, without that we cannot do a thing, okay, without a model of memory. And so my perspective in this is that we are focusing too much on operators, how to implement filters, how to implement neurons and all this to do some certain operations. But all this, they exist in a vacuum if we don't have a model of memory. Because in the end, we constantly have to read and write, at least in the standard computer science language. So I think we need to focus on this issue more, and we tend to avoid it because we don't know how to deal with it.
Well, just a couple of comments there.
Who's talking now? Okay.
Yeah.
One of your fundamental questions was understanding how things fit together.
Mm-hmm.
I mean, I think at least as far as living things are concerned, then Darwin gave the answer to that basically nature runs a whole set of experiments. The ones that fail die, and what you're left with are the ones that fit together. Okay? So yes. I think that's why in biology, why things fit together in the sense that you asked. I think on the issue of Turing machines and computing, I think because of the Turing machine, we've become very fixated on the single engine. We've built extremely powerful and complex machines on a very simple single-threaded model, basically. And we extend that painfully and slowly and with great difficulty into trying to understand systems that actually demonstrate a certain degree of concurrency. And I think that's the fundamental stumbling block when it comes to understanding the biology, because the biological solution starts from the opposite end. It starts from very large numbers of interacting components rather than a single central engine. And to understand the way that the biology, that the brain generates behavior, I think we have got to go to the other end, the other extreme, and try and understand building functional systems out of many very large numbers of interacting components. And this is part of the philosophy behind Spinnaker. I talked about the million cores. The goal there is if you have a million cores, you can't start from one and then think about two and then four. You've really got to start at the other end. And whether what you do with those is model neurons or interacting processes on a graph or swarm behavior or whatever, it encourages you very much to think from the other end and build models to help you understand how very large systems of interacting components can generate behavior or do something useful.
So I tend to agree with everything that both of you just said. I mean, with regard to sort of maybe making progress, I do very much think it's a good idea to have some good benchmarks that aren't MNIST, right, or ImageNet. We need some real benchmarks, and I think as a community we haven't really maybe invested as much as we should in that, because those things really, you can measure what you did after that and see if you're making progress. So at Brain Corporation, we do our stuff on robots, so I completely agree that, closing the sensory motor loop in the real world is a really big problem, and you get a totally different perspective when you try to do that. It's really, really hard. Unfortunately, when you want to build the robot today, you end up building every piece of it. And most of us are not roboticists, so that ends up being a challenge, and then hooking it up to the computer ends up being a challenge, and getting the software to work, of course, not to mention all the stuff that, maybe is your particular expertise. That's a big challenge for all of us, and we don't really, I think, yet have, if we had some more common infrastructure and benchmarks, I think we could, have a more, constructive argument about the things we're arguing about right now with me. I mean, I have my perspective, Jeff, you have yours. I mean, maybe we could, have a way of testing various ideas in a way that we could measure them.
So what would a benchmark look like? Okay, I mean, the problem is it's a very open domain.
The one that we focused on right now is basically tracking in video, because it's the simplest thing we can do that deals with time and has some simple motor output. okay? But if you look at sort of there are tracking benchmarks out there, but they're pretty small, right? And I don't think we've sort of gathered around the idea that maybe we should test all our models against some common benchmarks yet. And then you can go to other things like that. You can put it on a robot, and if the robot can track things, and maybe it can follow things, all right? So I think there are some incremental steps we could take toward building benchmarks.
Okay.
I just want to add that it's a very needed, this benchmarks idea is something that's very hardly needed by the community. And in Frontiers in Neuromorphic Engineering, there's a special topic on that. There's already half a dozen papers proposing benchmarks. So if you have some ideas, you should start proposing them as well there. The idea is to have like a encyclopedia with benchmarks for neuromorphic circuits.
Where is this? Oh, this is for neuromorphic circuit.
Neuromorphic systems and circuits. So it's Frontiers in Neuromorphic Engineering. It's a special topic. There's already a bunch of proposed benchmarks using dynamic vision sensor outputs and using robotic applications and things of this type. So
well, as a suggestion, I think one of the things maybe that the government representatives here, the people from the funding agencies and the national labs, could be a natural place to sort of, initiate and maintain that sort of infrastructure. It's infrastructure. We have to have it.
Yeah, on benchmarks, I would like to recommend language. Topics about language, because language is a code that the brains have chosen to communicate with other brains. If that code was not somehow friendly to the construction and the working of the brain, brains wouldn't use it. So it is something that is produced by brains to be consumed by other brains. So vision is difficult in that there you deal with the world that you have no control over. You just have to take the scenes the way they come, and so it's in that sense it's a much harder problem.
So I think, Todd, I think your point about benchmarks is great, and I think I was going to ask a question very related to that because, from my perspective at IARPA, just like when you were at DARPA doing Synapse, it's actually, I have the problem. It's like if someone gives you 5 minutes to give a talk, it's impossible to get what you want to say in 5 slides. But if you get an hour, it's trivial. It's like the opposite problem. I know how to spend $1 million. I know how to spend $250,000 on little projects here and there. I don't know how to spend $100 million, to really advance the field. And the opportunities that I see right now are in these 2 different bins. There's like the Synapse approach, which is build something big and hope you can figure out what to do with it later, no offense, which is great. It drove the field forward. We have this great hardware platform, but I don't know that we really know what to do with it quite yet. And the alternative is, right now the sort of in vogue is building deep neural networks in neuromorphic hardware because we know they exist and we know what to do with them, although then we have the opposite problem that we're not sure that really, they weren't designed really to be brains, so it's not clear that you really want to use silicon neurons to implement them as opposed to other specialized hardware that's optimized. And so, the problem that the question that I would ask the panel is similar to you. I need, for me to advocate for a new program, I need some sort of deliverable, with an application, with some task that I have a reasonable chance at seeing neuroscience or neuromorphic systems outperforming some other class of systems, in that task. And, or I need some reasonable belief that if I build this system with some fundamentally new, architecture dynamics, it can achieve something in particular. Not just sort of it's a new toy that we can figure out what to do with. So I'm curious if the panel has thoughts. You all do research in this area. You all, you all think about this every day. So I'm curious for the people in the panel and also just for the audience, what is that problem that, we see that we have some chance of making meaningful progress towards in, 5 years and $100 million or something on that order of magnitude that's sort of tangible and leverages what we know about the brain to really, make to be a significant advance over the other alternatives? Or does that even exist right now? It's a bad sign.
I can make a comment relative to the Synapse project and the experience there, sorry. So, you know, when going into the Synapse project, we say, okay, we're going to build a brain, right? And it's going to be this hardware and it's going to do everything, right? But, you know, as you get into it and you say, okay, if you're going to build a chip that learns, for example, you know, it's a really tough call about what capabilities to endow with that on that piece of hardware, right? And so in Synapse, we decided, you know, for this chip that IBM built anyway, that we should not do it. We should train it off chip somehow, and then, you know, use the chip to implement it after the training was done. And it wasn't what I wanted to do. You know, I really wanted to build a learning chip, still do. But the truth was it wasn't clear what to do. You could build a deep learning chip. Actually, we didn't know about deep learning at the time, really. I mean, we sort of knew, but it wasn't like sort of what it is now. So I guess we didn't really have that discussion. But now, you know, there are companies building deep learning chips, and maybe there are good applications for them, and I think there's merit there. As far as sort of the general purpose learning system, I still think we're conceptually impaired in some fundamental way.
So maybe, not that I have a solution to this question, Jacob, but I would say that neuroscience has actually a similar problem. So for a long time, we were looking at very stereotyped behavior that was well controlled, and it was relatively easy to, you know, to do an experiment and to really then study how certain neurons respond. But of course, a good example is actually C. elegans. You know, for a long time, people thought, oh, it just does this tumbling behavior sometimes and follows maybe some chemical gradients. Until then, you know, people like Corey Bargman started to study the behavior of this worm in a little bit a more realistic environment. And so I think if we just sit down on our desk and try to come up with good benchmarks, I feel that might not be the right approach. The right approach is really to study the behavior also maybe of simpler animals, and then use some of these capabilities that these animals show, and also use all our knowledge in machine learning and so on for really trying to categorize and to analyze this behavior, and maybe that could help to get to benchmarks. But I feel if we just sit down and come up with some benchmarks for neuromorphic systems, I have to look at this volume, I guess. But
if you haven't done it, you should read Thomas Kuhn's The Structure of Scientific Revolutions. And both the neuromorphic field and neuroscience are in this sort of pre-paradigm state. And he has a lot of good observations in that book about what that state looks like and nature. And you can easily recognize what's going on right here as being in that state. It would suggest, I think, that we shouldn't pick really one big project because no one knows. There's a lot of different opinions and so on. I think you can pick a general area and do a lot of little things and see what comes out of it, and that might be more productive. I don't know. I don't give out funding for these kind of things. But you know, if you wanted to focus on one area, such as sensory motor integration and behavior with sensation, instead of having a task, a grand challenge task, you might have a task of a competition on algorithmic approaches, or just theoretical contests in some sense, like what are the different approaches we might have to solving problems of sensory motor integration. Those can be quite small. I'm making this up, it's not something I'm suggesting, but at the moment it feels to me that we're not in a pre-paradigm state, we're not in a point where we can say, okay, we know the big problem, here's $100 million, 5 years, we're going to solve it. I don't think we're there yet.
So the White House recently announced a new challenge, right? That seems to resonate with what we're talking about here. In fact, that also suggests the benchmark, right? So that challenge was nanotechnology driven, but behind that is a deeper question of how do you build machines that are intelligent, that learn by themselves, that are good at learning inference. And one important aspect of that is those machines have to be extremely efficient, right? So do all this at the efficiency of the human brain. And so this would suggest benchmarks that are driven by not just performance, but also the cost, right?
But aren't you mixing things up there, though? I mean, you know, it may turn out that, you know, the cost efficient or power efficient may not be the right thing to focus on, unless that's all you care about. But if you're trying to get to some, I mean, it depends on what you really care about. If you're trying to get to some sort of larger algorithmic principles, then it could be misleading to say, well, I need to be the most power efficient as well. I mean, yes, brains are power efficient, but that seems to be, those are sort of orthogonal tasks, don't you think? I mean,
well, there's a reason why our brains operate at, say, 15 or 20 watts and not at the kilowatt, right? So we would not be able to walk
it's just a
around.
matter of that, you know, you need nanocomputation at the molecular level, and we just don't know how to do that. I mean, the computational principles by which the brain works, I don't think are related directly to cost, to power or cost. They are principles that exist on their own way, and then there's various substrates you can apply them to. So I wouldn't mix those two up. I think it'd be very confusing. In fact, I think that's part of the problem we see now in the neuromorphic space, and I don't work in that space, but, you know, people are, you know, this is not really a problem, but it's, you know, if you're focusing on some aspect of the neural circuitry, but if you don't have a larger theory, you don't know if it's going to work or not. So these are sort of separate efforts. You can say you can work in device physics, and you can focus on those things, but you can work on algorithmic things. But I actually personally think it's too early to merge those two at the moment, because you know, if you don't have a real paradigm on the theory side, you might be doing the wrong things. I guess I'm just reacting to. I think you should separate out the power efficiency and cost from separate problems from. Basically computational and algorithmic approaches to brain theory. I don't think they're the same thing. Sorry for interrupting you.
Well, but I mean, you know, the name of the conference is Neural Inspired Computing, and I mean, we're trying to find neural principles that will give us 5 or 6 or 7 orders of magnitude improvement in efficiency. So, I mean, just to put the context sort of out there. I mean, I understand what you're saying, but you know, a lot of this discussion has been pretty specifically about the brain and AI and neurons, but NICE is about improving the efficiency of computation fundamentally, using neural principles. I don't know, I just thought that needed to be stated.
Also, well, I think that if we have the same constraints that the brain has, we might restrict the space of possible solutions, and we might find...
Maybe. We might, but maybe not.
We might limit our theoretical exploration because we're always trying to stay under this bar of power. Sorry, I already finished this. I was saying we might limit the space of theory we explore if we're constantly trying to keep within power constraint. And so by mentally separating those, it would give us the freedom to explore the capability space. And of course, ultimately, if we have the brain figured out, we're going to get both. But, you know, just having some clarity about what direction we're working on at the time.
It might help you individually thinking about power to come up with some principles that help us figure out brain theory. I'm not saying that can't happen. I just don't think, you know, we all have to take our different approaches to this thing and see where they come out. But I don't think we can say that's the, I wouldn't say that's a common goal that we have to solve both of them at the same time. It may be helpful for you. It's not helpful for me. I actually don't find it helpful to think about that. I think it's far more helpful to think about representations and sparse representations and so on. And yet some people don't think that's important. So we all have to do our own thing until the paradigm emerges.
I think I agree with the argument here, actually. I think what we're in danger of doing is worrying about the fuel efficiency of the engine of the car before we invent the wheel. Right, we need to know how the thing works. I mean, the reason I emphasize energy efficiency for Spinnaker is really just a cost of ownership issue, right? It's not fundamental to what we're trying to do. It's just that if we don't worry about energy efficiency, it'll cost too much to run, and we won't be able to use it as much. We're orders of magnitude worse than biology, and that's inescapable with the approach we've taken.
The reason I like Spinnaker is because it focuses on connectivity, and connectivity is a problem we're going to have to solve in messaging.
Yeah.
I hope you're looking like skeptical. I hope that wasn't. No.
No.
Okay.
Carry on.
I mean, And so I can almost absolutely say for certainty that the future electronic brains are going to have massive connectivity problems, and so to the extent that we can start thinking about that in a principled way, in a generic way, is going to be helpful. I think that's going to be more helpful than to say, well, how do I get these so many joules out of a synapse or something like that. I mean, that's stuff we don't know yet. So we can make some broad guesses here, but if you look at the world of neuromorphic computing, it's sort of two buckets. You've got sort of the device physics people, which I love them. I think a lot of really cool stuff there. And then you've got people like Spinnaker who are really looking at sort of large connectivity architectural issues, not worrying about the details of the neurons and the synapses or any of that stuff. Those are two different approaches. I think the approach that Steve has been doing is probably the one that is going to help us, is more clear right now that it's going to be useful, where the other stuff is not clear yet.
I mean, I disagree. I don't think we're going to have a problem with emulating the connectivity of the brain in hardware, in the next few years, because I mean, if you look at it like nano crossbar, and especially if you go into the 3 dimensions, I mean, you only need order 10,000 or so local connections anywhere in the brain. You have to emulate the macroscopic modular structure of the brain. But I think that the technology is already almost, there to capture the local connectivity.
Well, maybe local, but we're talking about very complex systems with a huge number of connections. So.
Well, it's one thing to self-organize, all the regions of the cortex and all the subcortical regions, and explain how it becomes self-organized. But I think that the physical connectivity is, pretty close to being able to be captured by, technology that's on the horizon.
Maybe. I'm glad you're optimistic about that.
So, have you done any chip design?
No.
The one thing I want
so
to...
the big problem in chip design is getting the number of signals on and off the chip. Yeah. I/O is the limit.
Yep.
The reason the neocortex is so big is the white matter. It's not the synapses, it's not the neurons, it's the axons that are connecting things together. And there, it's basically like an old Cray computer. They have all the wires connecting everywhere, all over the place. And you've got a 3-dimensional substrate with blood vessels and all this stuff. We don't have that in silicon, and you can't do that.
No. And in fact, biological brains obey a version of Rent's rule. Right?
I don't know that rule.
Yeah. Rent's rule is an old IBM rule that the number of I/Os you need scales with the number of functions on the chip as a power law. Okay, and if you observe the ratio of white matter to grey matter in the brain, it observes Rent's rule. This was Dan Greenfield's thesis at Cambridge. He did a study of this. So Rent's rule applies to brains as well as chips. And I/O is a headache. It's less of a headache for biology because it can use 3 dimensions. Probably.
Yeah.
So I like the benchmarking discussion. I want to throw a different angle on it. I think that it's very interesting to look not into computer science, not into neuroscience, but into neurology when trying to think about benchmarks. And the reason I say that is nature's done a tremendous number of experiments for us. They have done experiments with white matter. It has done experiments with, receptor, you name it. Somewhere there's a disease in neurology that futzes with one of these systems that can be observed clinically in terms of a deficit. I have some reason to believe this will work because the work that we did actually started dealing with cerebral palsy and then moving on to things like autism. The beauty of doing those kinds of benchmarks is because you have 2 ways of testing the model. You have the ability to test good, and then you have the ability to take some of these injuries that are extremely well defined, apply those injuries to the model, and see if you get a result that comes out that matches anything that matches the observable result of these types of diseases. So I want to throw that out just for discussion that I think benchmarking is critical. But I would suggest we think about it from a neurology perspective as opposed to a neuroscience or computer science perspective.
So one of the things that really intrigues me about brains is related to neurology, which is the fact that we can pour alcohol into them and they still work.
Let's go
This does bring this thought to mind that it's probably a good time to conduct that experiment.
I would second that motion.